Okay, this is part 2 of Unit 3, Topic 1. In part 1, we talked about the theory behind the nature of light and the photoelectric effect and the quantum theory, if you like. Now we're going to take a look at some examples from old public exams that cover the same thing, the same topic. Okay, so we've already done the theory behind it and some of the formulas behind it. Let's take a look at how that is applied now. So, which phenomenon supports the particle theory of light? And really supports the particle theory of light only. In other words, which one of these is exclusive to particles? That would be the photoelectric effect. Diffraction, interference, both of those are specifically wave theory. Now, refraction is an iffy one. You can show refraction with particles too, but not very well. The photoelectric effect is the one that's exclusive to particles. The minimum energy that will allow electrons to be ejected from a metal surface during the photoelectric effect, by definition, we call that work function. That's simply work function. That's it. No more to it. Then we have our first calculation, and that's using Planck's equation. E equals h times F. H is the constant, and the value of this constant is given on your formula sheet, your data sheet that you get with your exam. And the frequency here is given in the question. It's that. Multiply those together, go with 2 significant digits, and you get, 3 sig figs, you get this. Okay, 6.63 times 10 to the negative 20. And that's measured in joules, okay? That formula calculates joules of energy. So the answer then obviously is D. The answer is D. Moving on. What wavelength has that much energy? Well, we're going to use the other version of the formula now. Instead of saying h times f, we're going to say hc over lambda. And if I want to know what lambda equals, I'll just rewrite the equation as hc divided by E. So we plug in our numbers again, 6.626 times 10 to the power of negative 34, that's Planck's constant, straight off the formula sheet. Speed of light, or c, also straight off the formula sheet, all divided by the energy, which is given in the question, 4.70 times 10 to the power of negative 25. You do that and you get this answer right here, 0.423. 0.423. And the next one is kind of interesting. This is a level 3 question, really. E equals h times f. That's the way you're used to seeing the equation written. But if you rewrote it like this, as h equals E over f, then h would be the ratio of energy to frequency. Okay, there's your ratio. Energy on top, frequency on bottom. So the ratio is equal to h. And h is known as Planck's constant. H is Planck's constant. Then I've got the wavelength of a photon having this energy. Well, that's the same as the first question on the page, except my energy is given in a different unit. Look, electron volts. And you may remember from the previous unit, okay, unit 2, that electron volt is another unit we can use for energy. So I can start again by saying simply that lambda equals hc divided by energy. Same thing I said up top, hc over energy. Okay, and I plug in my value for h, 6.626 times 10 to the power of negative 34. C, 3.00 times 10 to the power of 8. And I divide it by my energy, but in this formula the energy is supposed to be in joules, but it's not. So I have to convert it to joules. So I take my 2.12 electron volts and I multiply by the conversion factor, which can also be found on your formula sheet, on your data sheet. 1 electron volt is equal to essentially the electron charge, 1.602 times 10 to the negative 19. And we do that calculation, we get 5.85 times 10 to the negative 7. And they got here 5.86. That's a rounding thing. But that is the right answer. That is the right answer. It's off a little tiny bit because of rounding, but watch for that. When you're off by 1/100th like that, not very significant. Don't worry about it. Let's try another one. This time we got a graph. This is a level 3 question this time. Most of the ones where you're dealing with graphs end up being level 3s because you're not used to looking at it in this way again. So we want to know, what is the unknown metal if light with a wavelength of 1.87 times 10 to the negative 7 meters shines on it and the maximum kinetic energy of the ejected electrons is 2.5 electron volts? Well, the first thing I'm going to do is I'm going to draw a line across here. Here's 2.5 electron volts right across there. Okay, and I'm going to make that line red. At least I'm going to try to make that line red. There we go. So our line is red. Now, I need to know which of those metals, A, B, C, or D, has this wavelength. This wavelength right here. 1.87 times 10 to the negative 7. So, on the graph, I'm showing frequency. So what I need to do is I need to change that wavelength I'm given into a frequency. And frequency, remember, equals C over wavelength, C over lambda. So 3.00 times 10 to the power of 8 over lambda, which is 1.87 times 10 to the power of negative 7. You do that, you get a frequency of 1.6, 1.60 if you keep 3 sig figs, times 10 to the power of 15 hertz. So that's right here, isn't it? Just watch. Now I'm going to draw another line. I'm going to make this line green. And I'm going to go up from 1.6. Okay, I go up this way, and now you can see where those two lines intersect. That's the point I'm looking for. So in other words, I'm looking for this guy right here. Look, there's the point they intersect. That's metal B. So my answer is metal B. That's how you have to do it. Okay, so a little bit of work to it. And level 3, because it's a different way of looking at that. It's a different way of looking at the photoelectric effect, right, from a graph. It's a little different. Let's try the next one. This one has to do with increasing the intensity. Now when we increase the intensity, that has no effect on energy at all. No effect on energy. So the energy stays constant. So we know the answer is not C or D. Right away we can rule that out. But the thing that does happen if we increase the intensity is we will increase the number of electrons that are being ejected. In other words, we will increase the rate. We increase the current is what happens. If we increase the brightness of the light, we get more current. So the answer is B. The rate increases. More electrons ejected per second. But the individual electrons don't have any more energy than they had before. Next one, by what factor does energy of a photon change if its wavelength is cut in half? Remember that energy equals hc over lambda. There's your formula. So in other words, energy and wavelength are actually inversely proportional, okay? Energy is proportional to 1 over the wavelength, 1 over lambda. So what we do is if the wavelength is halved, that's like saying 1 over a half. And 1 over a half is equal to 2. So the energy changes by a factor of 2. That's the easiest way to look at that one. Next. This time we're going to use the photoelectric effect equation. Okay, and because we're given a wavelength, we're going to say hc over lambda is equal to Ek, kinetic energy, plus work function. That's the photoelectric effect equation. Now on the formula sheet it's given as HF equals. But remember, we can swap hc over lambda if we're given wavelength instead of frequency. We're allowed to do that. So essentially what you have then, if you're trying to find the kinetic energy, then hc over lambda, take away work function, is going to be equal to Ek. So here's what Ek equals. Let's plug our numbers in. 6.626 times 10 to the power of negative 34. That's H. C is 3.0 times 10 to the power of 8. Divided by the wavelength, which is 1.7 times 10 to the negative 7. Then I need to subtract my work function. But now I got a slight problem, because my work function is in electron volts. I need joules. That equation works out energy in joules. So what I do is I take my 4.56 electron volts and I multiply it by the conversion, which is this. I multiply it by that conversion factor, 1.602 times 10 to the power of negative 19. And again, that conversion is on the formula sheet. 1 electron volt equals that many joules. So when we plug all that together and do the calculation, we get this answer right here. We get that answer. By the way, one of the other answers there is what you would get if you forgot to convert your units. Okay, so do be careful with that. Next one says, which best describes the wavelength of photons with this amount of energy? So wavelength equals hc over energy. We've written that equation down a couple of times already. So let's do it. Let's figure it out. H is still Planck's constant. It hasn't changed since the last time we used it. It's still that. And 3.00 times 10 to the 8, that doesn't change. Divide that by energy, which is 7.95 times 10 to the power of negative 15. And that will give you 2.50 times 10 to the power of negative 11 meters. But you'll notice we're given nanometers, so to change that to nanometers, you would multiply that, or divide that by 10 to the negative 9, and that would give you 10 to the negative 2, or 0.0250 nanometers. So we know the answer is not C or D. We know it's either A or B. Both of those have the same number given. But here's the key, or longer or shorter. Now you got to think, what happens to the energy when we change the wavelength? Well, we want the energy to be that or less. So how would I get less energy? I would have to increase the wavelength, because remember, they are inversely proportional to each other. If the energy goes down, the wavelength has to go up. So that tells me it must be the or longer choice. That has to be the answer. And then this one here, E equals hc over lambda. I don't have to rearrange it this time. Plug in our numbers, 6.626 times 10 to the power of negative 34, Planck's constant. I multiply that by C, which is 3.00 times 10 to the power of 8. Then I'm given my wavelength, this time in nanometers, so do be careful. I have to multiply that by 1.602 times 10 to the negative 19. No, what am I talking about? I'm getting ahead of myself here. I have to multiply that, sorry about that, by 10 to the power of negative 9. I was thinking ahead to the next step there. And when I do that, I get this amount of energy. I get 4.4 times 10 to the power of negative 19. However, that's joules. You'll notice that all the answers there are given in electron volts. This is actually 4.42, by the way. It's actually given in electron volts. So I have to convert my joules to electron volts by doing this, by dividing by the conversion factor. Now 1.602 times 10 to the negative 19, and you do that division, you get that answer right there, 2.8 electron volts. So there's some examples of multiple choice questions. And you could see questions like that on your public. Now, they're not all going to be there, obviously, but there will be questions there similar to at least some of the ones we just did. Okay, the same types of problems show up year after year. It's the same course, same objectives, same thing has been taught. The questions don't change all that much. The level 3 ones change up a bit, but the level 1s and the level 2s, you've seen most of them before. If you go back over the old publics, there's not too many surprises there. Here's another level 3. This is a level 3 from part 2. Now this one's a little bit challenging. But the most challenging part of this one is the actual solving of the equation. So we got a light source with a wavelength lambda, illuminates a metal, and ejects photoelectrons with this energy. Another light source with a different wavelength, that's only half, shines on the same metal and ejects photoelectrons with a maximum kinetic energy of this. So because it has a smaller wavelength, those photons have more energy, and therefore they give those electrons more kinetic energy. Okay, but we're asked to calculate the work function. Well, what you got to remember is this. The work function, because it's the same metal, the work function is the same both times. Because the work function depends on the metal, not on the wavelength of light. So the easiest way to start that one is to do this. We say the work function for the first one is equal to the work function for the second one. And that's going to be hc over lambda minus ek. And we had that formula just a few minutes ago. Okay, and the two of them are equal. The hc and the hc, that doesn't change. It's the other things that are different. So what we do is we start plugging in what we know. The only thing we don't know here is lambda. I know everything else but. And what you got to notice here is that the energy was given in electron volts. So I have to convert that to joules by multiplying by 1.6 times 10 to the negative 19. Technically it's 1.602, but I'm not going to worry too much about that. Okay, so there's your setup. There's the setup of the equation. So there's the first step in solving that. Okay, we condense it together a little bit. In other words, multiplying Planck's constant and the speed of light gives you this number. Multiplying this and this gives you this number. So here's a simplified version now of that formula. So like I said, the rest now is math. The rest of this is math. We just got to solve the thing. So here we go. What I do now is I bring the two lambdas to the same side. Now, what they did there, you'll notice, this was 1.99 times 10 to the negative 25 divided by lambda over 2. To get rid of that over 2, we multiplied by 2 on the top. And that's where the 3.98 times 10 to the negative 25 came from. Okay? And then we brought the other ones, the constants, over to the other side. So that boils down to this. Okay, and all you're doing is simplifying. Okay, that's all we're doing. Like I said, the rest is math. There's the wavelength. That is the wavelength of the original light source. Now that we know that, then all we got to do is use this equation again, hc over lambda equals ek plus work function. Solve for work function. All right, we plug in everything we know. Now we know the wavelength along with everything else. And you get this. The work function is this in joules. Or if you want to change that to this, you can do that too. Doesn't matter which way you do it. Doesn't matter which way you do it. It's easier to just leave it in joules because that's what the formula calculates it in. Those are the units that it uses. So that's it. Done. Finished. Let's try this one. This time it gives us the stopping potential. Remember that? We talked about stopping potential equals kinetic energy. So stopping potential equals kinetic energy. Or EV stop, I should say, equals kinetic energy. So all we got to do is take this, 7 volts, multiply it by the charge on an electron, and we know the kinetic energy. We know the kinetic energy. So here's all we got to do. I'm going to say, first of all, energy of the photon equals WO plus EK. So HF, which is the energy of the photon, and we're given the frequency, so we do use the HF. WO we don't know, but V times Q, or the way I wrote it before was, instead of saying that, I said E times V stop, because the charge is an electron. So now all we got to do is plug those numbers in. So we've got Planck's constant, 6.626 times 10 to the negative 34, times F, which was given, 3.0 times 10 to the 15. And on the other side, I've got the charge on an electron, 1.6 times 10 to the negative 19, times the 7 volts. Simplify that, and you have your work function. Okay, and you can see what that question was actually worth on this particular test, this particular public. It was worth a total of 3 marks. 3 marks. So there's your work function. Again, in joules or electron volts, it doesn't matter which unit you give it in unless it specifically tells you to use one unit or the other. They're both acceptable. Unless it specifically said to give it in electron volts, you do not need to change it. It's not necessary. It's only an extra step that risks making a mistake. So if it's not asked for, don't do it. Not a good idea. Let's try this one. The maximum wavelength that will cause photoelectric emission from a metal surface with a work function of. So we're talking about the threshold now. And remember, what you got to remember is at the threshold, there is no kinetic energy. Okay? The maximum wavelength is at the threshold, or the work function. In other words, EK is 0. So now, all we got to say is the energy of the photon is equal to the work function. It's equal to the work function. So I'm going to say HC over lambda equals work function. That's the hardest part of this question. Once you get that figured out, it's just a matter of plugging in the numbers. So if I rearrange that, lambda equals HC over work function. Plug your numbers in. Don't forget to convert your units, right? Because that work function was given as 2 electron volts. So I do have to multiply by 1.6 times 10 to the negative 19 to do the conversion. Okay, and once I've done that, the rest is easy. There you go. There's the answer. 6.21 times 10 to the negative 7 would be that maximum wavelength. And remember, maximum wavelength gives minimum energy. Okay? So that's where the cutoff would be. Anything higher than that wavelength would not be enough energy to cause the photoelectric effect to occur. All right, here's a different type of one. In this one, you were given a photoelectric experiment, light was shone on a metal surface, and the following data was collected. Frequency of light, maximum energy of electrons. Okay, so at all these frequencies, these were the energies. And you were asked to draw a graph of that. So here's the first part. Graph the results. Okay, so EK max on the side, frequency on the bottom. This part, by the way, was already drawn in for you. So all you had to do is plot these 4 points, draw a line of best fit that comes all the way down to the x-axis. So you can see where the intercept is. Because this intercept is the threshold frequency. Because that is where there is 0 kinetic energy for the ejected electrons. That's what we call the threshold frequency. And that's good because in the second part, you were asked to find the work function. And remember, that threshold frequency, that gives us the minimum energy needed, which is actually equal to work function. So all we have to do is figure out this. WO equals E, because EK is 0, right? At that minimum, to find the work function, we use that minimum. So we do this, WO equals HF, very simple calculation. You take this F, that's the x-intercept on your graph. That was the minimum frequency. That is when EK was 0. That was when EK was 0. So you do that, there's your answer. And again, you'll notice it's given in joules or electron volts because it doesn't matter which units you use. They're both acceptable. They're both acceptable. Okay, one last question. This one is an explanation one. And this one ties in with the STSE for Unit 3, which is called the physics of movie sound. Movie sound, at least in the old-fashioned type, right, when sound is encoded, for example, on a film strip, it's usually done in a series of light and dark bands. And light from the projector bulb then falls on a photocell and causes the photoelectric effect to occur. So what happens, it says, is a bulb in a movie projector is replaced with a bulb with the same intensity but a different frequency. There's the key, different frequency. And the sound doesn't work. And the reason the sound doesn't work is because in a lot of movie projectors, the sound depends on the photoelectric effect. And you would have had to read the STSE to know that. So it's a good idea to go back and read over those 3 STSEs. So with reference to the photoelectric effect, and the hint is there, right? With reference to the photoelectric effect, explain why that occurs. What's the problem? How come there's no sound? Well, first of all, in order for the photoelectric effect to occur at all, the energy of the photons must be greater than the work function. And I guess with the original bulb, that wasn't the problem. The frequency was high enough that the photons had enough energy. So I guess what happened was, if we change the frequency, in this case we put in a lower frequency bulb, then the photons do not have enough energy to bump electrons off the surface. So therefore, no electrons means no current, means no sound. There's your 2 marks for that question. Okay, so like I said, you would need to realize in the STSE, that is the only real important thing in that STSE. You need to know that movie sound, movie projectors, do rely on the photoelectric effect for the sound. The soundtrack is actually encoded on the film in that way. Now, a lot of them are going digital, and that's a little different. But most movie theaters still use that system right there. That brings us to the end of the questions on this topic. So we're going to stop right here, and I encourage you to go on and view topic number 2 as well. Topic number 2 will be a little bit shorter. We'll do all that one in one part. But that's where we'll end for now, so good luck, keep studying, keep working.